Are you ready for some science? Are you ready for some gamma rays in your body? No, maybe not. Okay, guys, we are going to begin. So welcome to Astronomy on Town. Sorry, I need to read. I have some aids. So we are going to start with Dr. Alberto Rosales here. Woo! So he is originating from Oaxaca, Mexico. Oaxaca, Mexico. Alberto has a background in mathematics, in astronomy, in science fiction, and physics.
Yes.
And he completed his bachelor and master students at UNAM, Universidad
Autónoma de México,
in Mexico City. And then he did a PhD in the University of Durham in England.
Yes.
Specializing in astrophysics and gamma-ray astronomy. Alberto is currently a postdoctoral researcher at the Laboratoire de Physique Nucléaire et de Hautes Énergies, or LPNHE. LPNHE, or something like that, at Sorbonne University and at the Observatory of Paris. So he will introduce us to gamma-ray astronomy and guide us on a journey across the high-energy universe. So welcome, Alberto.
Thank you.
Thank you everyone.
Excelente.
El de abajo.
El de abajo. Vale.
Thank you everyone. Let me try this. 1, 2, 3, 1, 2, 3.
Ew. Oh. Ooh. Thank you. I also wanted to do that. So we're going to start with the talk. We're going to do a little trip for the high and very high energy universe. And I'm going to talk about gamma ray astronomy. So, for the people who don't know, it's not changing, but
Okay, sorry. It's not on? Oh, be
Okay.
closer to this side.
okay, I get closer. I'm going to start with a question. What comes to your mind if you hear gamma rays? Gamma rays. So this is for the broad people. Some people, the first thing that they think is Star Wars, the Death Star. Yeah, Star Wars, Darth Vader. Other people think about movies. So if you don't know, there is a movie called Gamma Rays. It's actually a French one. So you can search for it and improve your French. Most of the people, especially the young generations, they think about the Hulk, Dr. Bruce Banner, who suffered a very interesting accident related to gamma rays, and after that he became the Hulk. And for the very, intelligent people, conocedores, they think about the beer. There is a gamma ray beer, so if you haven't tried it. It's really good. It's from a company called Beavertown Brudo. So this is what people think. This is what people think when we when they hear the word gamma rays. But there is like a broad of things. What is exactly gamma rays? So I'm gonna show you this standard picture. This is what you usually get in school or at university when they explain gamma rays. So you can see the electromagnetic spectrum. And at very low energies, you have something that is called radio. So we have radio waves, just like the ones that you hear when you turn on the radio, AM or FM. Then we have microwaves, so like the ones that we use at home in the oven. Then there is the infrared part, which is related to the heat. So there are some infrared cameras that can detect the heat from objects. Then we have the visible light, which is the one that we can observe with our very own eyes. After that, we become a little bit higher in energy. There are X-rays, just like the ones that they use in hospitals. And because these are more energetic, they can cross the They can cross the skin and some of the organs, but the bones that are more dense, they cannot cross the bones. So you can have an X-ray image of your bones. There is also radiotherapy done with X-ray and some energetic radiation. And then at the very high energy extreme, we have gamma rays. So if you look at the spectrum and you see at the numbers, we have, let's say in wavelength, 10 to the 2 on one side, and then 10 to the minus 21. So these are more than 20 orders of magnitude. And you can see how it changes this order of magnitude from a building to the smallest thing, smaller than an atom, smaller than an atomic nuclei. So depending on the part of the spectrum that you are, you can see different stuff. And in terms of gamma rays, it can be described as the most energetic light in the universe. So it has a really high frequency, it has a very low or very short wavelength, and because of that, is the most energetic light in the universe. That is the definition that you can keep in your mind for gamma rays. Now, where can you find gamma rays? In case you don't know, well, we're going to talk about astronomy, so there are going to be a series of objects, astrophysical objects, that produce gamma rays. Some of them are called active galactic nuclei, which is a very technical term, but what it means is there is a supermassive black hole that is like the main engine, and from this supermassive black hole is like to have like a huge accelerator. It's like a particle accelerator. So when particles get accelerated around this black hole, they interact, they have hadronic interactions, and because of that, they're producing gamma rays. There are other phenomena that can produce gamma rays in outer space, specifically like extragalactic, but also in the galactic. So we have supernova and hypernova, and also gamma ray burst, which is going to be the next talk. So just live with this in mind. There are astrophysical objects which are kind of weird, but they are very energetic and they produce gamma rays. Where else can you find gamma rays? In the sun flare. So basically, the physics of the sun is a nuclear reactor, but it's a fusion reactor. So we have nuclear reactions in the sun, and from those nuclear reactions, they come gamma rays. And when we have sun flares, we can also detect those gamma rays with the detectors at Earth. Nuclear reactors. If you go to a nuclear plant, they have some isotopes that are emitting gamma rays, and from those isotopes you can produce electric energy. But if you go to a nuclear plant, you can find gamma rays, and it will be very characteristic because all these nuclear elements, these isotopes, are inside of a pool, and this pool, it's glowing in a blue color. That is because something that is called the Cherenkov effect, and it's very important, as we will see. So also keep that in mind, Cherenkov effect. And if you want to see this Cherenkov effect in real life, you can only see in these two places on Earth: nuclear reactors and something that is called gamma beams. So for the gamma beams, these are used in medicine. These are also elements. They usually use cobalt 60, which is an isotope, and it's emitting gamma rays. So they have these bars of cobalt 60 inside of a pool, and basically the water is absorbing all the radiation coming from this element. When you put them out, all the gamma ray radiation will fool the room. It will fool the room in which these things are, and they use it in medicine because of sterilization. If you have medical equipment or even the stuff that you put like in a sterile room for surgery, you put them like 20 minutes in a gamma beam, and it kills everything. So it's very useful for medicine. And the other thing, the other place in which you can find gamma rays is in nuclear explosions. So if you watch the movie Oppenheimer, you're probably familiar with that. And there are again nuclear reactions, gamma rays coming out, and we can have gamma rays from the nuclear explosions. Now, let's change, yes, to gamma ray astronomy. So what is gamma ray astronomy? I will put it in simple words. It's the study of the astrophysical sources and phenomena in outer space that produces gamma rays. It's a plain, simple definition. Everything that is out in the universe, outer space, that produces gamma rays and that we can observe them or detect them with the instruments that we have counts as gamma ray astronomy. And also keep in mind the previous definition. Gamma rays is the most energetic light in the universe. So the question, of course, is why doing gamma ray astronomy? So I'm quoting here a collaboration that I'm working with, which is basically a collaboration of a lot of scientists. And the official webpage says, to unravel the mysteries behind the cosmic particles, supermassive black holes, dark matter, and physics beyond the standard model. The possibilities for entirely new discoveries are endless. And it's true. It's true. With gamma ray astronomy, we can just test the theories that we have right now, the models, the physics models that we have. And also we can discover new stuff. And there's a lot of people working on these topics, some of them actually in this room. And we're trying to answer some questions that have been around for, I don't know, the last 100 years. And by doing gamma ray astronomy, we can shed some light into those questions, into those mysteries. Gamma rays are also produced by the hottest and most energetic objects in the universe. So I think it's an inception thing because I'm studying that and I think I'm hot and very energetic. So for me, it was a natural choice to do gamma rays. Here, this is a gamma ray timeline. So it's a very new stuff. It's really new. It doesn't have like in physics. If it's 100 years, less than 100 years, it's kind of new. So you can see here that in the 60s, that is the point in which the first generation of the telescopes, the ground-based telescopes, were built. Also in the 60s, there were some people doing physics experiments with balloons. So they were put some detectors into the upper atmosphere, and they were trying to see or trying to detect something that is coming from outer space. In the late 60s, something happened that it was revolutionary for gamma rays, and this was in America, in Arizona. So they built a 10-meter telescope, which is called Whipple. And it was the starting operations in 1968, and it was the start of a revolution because it's the technology that we use right now. In the 60s as well, there were some satellites which are called VILA. So the VILA satellites were programmed specifically to detect GRBs, which we are going to hear more about it. The Apollo missions, we all heard about this. Apollo missions going to the moon, 1969. Well, these missions, specifically the 15 and 16, discovered the gamma ray diffuse background. In the spaceships built by NASA, there were some detectors, and they were detecting this gamma ray background from the universe. Then, 75 to 81, there was a satellite, which is called COSB, and discovered 25 sources of gamma rays. At the moment, nobody knew what was those type of sources, but they were discovering something. Then it comes again a period of construction, and in the 80s and 90s we have a second generation of telescopes. Everything was led by the Whipple Observatory, but it was the beginning of a new era in telescopes. Another satellite, which is called the Compton Gamma Ray Observatory, CIGRO. It was also very useful to map the sky and get a vision of the universe in gamma rays. And then it comes the modern era. After the 2000s, we got a third generation of telescopes, which are currently operating. I'm going to show them to you in a while. HESS, Kangaroo, Magic, Veritas. Those are the telescopes that are currently working on Earth, like ground-based. There are also a series of satellites, Swift, Agile, Fermi. So in the early 2000s and up to now, these things have been operating. Some of them are not longer anymore operating, they have been decommissioned. But fortunately, for 2020, we have a next generation of telescopes that are currently being built, which is called CTAO, Cherenkov Telescope Array Observatory. And you're going to hear that a lot because basically that's the collaboration that I'm working for, and they're paying me to say that name. So you're going to hear that a lot. So, like I said, it's the time for the sponsors and announcement and marketing. So we're going to introduce the Cherenkov Telescope Array Observatory.
It started more than 400 years ago when Galileo first used the telescope.
This is a need of the human being, the human curiosity.
If you look at the electromagnetic spectrum, on the low energy side we have infrared and radio waves. On the high energy side we have X-rays and gamma rays, light with extremely high energy.
Gamma rays go to the most explosive, massive effects. If you want to explode the high energies, you need to do it through gamma rays.
With gamma rays we can probe fundamental physics, we can look for dark matter.
Well, seeing gamma rays is kind of tough.
We don't see the gamma rays directly. High energy gamma rays produce Cherenkov light.
Gamma ray runs into the Earth's atmosphere, makes this sparking cascade. That's where this Cherenkov light comes in.
Let's say it's really a flash that lasts a few nanoseconds.
And we try to capture this Cherenkov flash, which is ground-based observatories.
In CT, we can study origin of cosmic rays.
Gamma rays are useful in the sense that you're looking at the highest energies, the most extreme processes in the universe.
Really powerful probe of what's going on, sort of at the frontiers in terms of this energy range that we know and so forth.
The final question is, how can we do all this? From the very beginning, the idea was we want to see the full sky, and that means we need two sides. The north side will be on La Palma, and the southern side will be in Chile, the world's two best astronomical sites.
CTAO has a tremendous energy range. We span many orders of magnitude in energy. We make use of different sizes of telescopes. We deploy three types of telescopes.
Each of them is optimized for a specific energy range.
A large size telescope, they measure low energy gamma rays. This has a diameter of 23 meters. That's because the flash of Cherenkov light produced by very low energy gamma rays. It's a very weak flash of light, 200 mirrors, around 100 tons.
Within 20 seconds to any position in the sky.
We need very special cameras, very precise optics. The camera is fascinating, 2.5 by 2.5 meters and weighs 2 tons.
With exposure time of a nanosecond, which is a million times faster than any normal camera. You sort of take a billion pictures per second.
It's the main part of the observatory of the medium-sized telescopes.
They have 12 meter diameter. They're devoted to study the intermediate range of energies.
The kind of core energy range of CTO around atto-electron-volt. The SST is the smallest telescope, no longer than the South for scientific reasons. The highest energy gamma rays produce a lot of Cherenkov light and have relatively modest-sized telescopes with a huge collection area.
A spectacular distribution of telescope.
The other big part is software.
There's no way you can save all the data, so the trick is really to recognize in real time if there's something which looks interesting.
It's a lot of data, so we're talking about petabytes a year. It's quite a bit. Where we are now, we have advanced prototypes of all the elements. We have a prototype on La Palma on the northern side, and it is so beautiful.
There are many telescopes to construct. This is the start of the game. It's not a minor challenge.
There's quite some hurdles to be taken. One of the big challenges is just the scale.
1,400 people. There's a lot of varied expertise. There's nothing we can build on a national scale.
instead of having an array telescope, because you have an array of scientists, and that makes the whole image more complete.
10 years, I think more than 10 years, we started doing a design study.
There is many things that we expect to see. I think the most interesting would be the things that we are not expecting to see, not the unexpected.
We have to admit, we don't know what most of the universe is made of. We have no idea.
You end up discovering something that you were not even foreseeing.
In the end, the great discoveries were never really ever what was originally proposed.
Wow, a round of applause, please. So, as you have seen, it's a collective effort. There's 1,400 people from many countries in the world, many institutions, putting a lot of money to build these arrays. One is going to be in the northern hemisphere in La Palma, the other one in the southern hemisphere in Chile. And it's a collective effort. Like to make this type of projects, you need a lot of time, a lot of people, physicists, mathematicians, engineers, lawyers. You need a lot of lawyers to build this type of stuff. A lot of money as well, yes. So let's change the next one. So this is how it started. This is the first Cherenkov detector used by Galbraith and Jelly in 1953. That thing over there is the first gamma ray telescope built on Earth. And it was a 25 centimeter parabolic mirror with a PMT. A PMT means a photomultiplier, so it's a detector. And it was attached in the focus inside of a garbage can. This was built in England in 1953. And this is how it's going now. So this is part of the stuff that you saw in the video. This was a photo taken in 2018 and is the inauguration of the first LST telescope. LST means large size. So it's one of the big telescopes that we're going to have in La Palma. There are going to be another 3. They're building it at the moment. And you can see there were around 200 people from 10 different countries in collaboration just to construct this prototype, this telescope. And it's beautiful. It's 100 tons moving to any point anywhere in the sky in less than 20 seconds. So in terms of engineering, it's a challenge, and everything is working smoothly. So it's just a miracle of modern technology. In gamma rays, we have 3 types of detectors, 3 types of observatories. One is space-based observatories, so satellites. These are missions that are launched basically for NASA and the European agency as well. And we put some detectors into a satellite, we launch it in space, and they orbit the Earth, and they can give us a picture of the sky in gamma rays. The other telescopes, the ones that I'm talking about and that I'm more familiar with, and the talk also is related to this, is the Imagine Atmospheric Cherenkov telescopes. So it's something very specific, just to say that we're going to look at the atmosphere. There are going to be gamma rays coming in the atmosphere, and they're going to interact with the atoms in the upper atmosphere. Because of that, they're going to produce a cascade of particles. These particles emit Cherenkov light, which is the stuff that I was talking before. You can recognize the Cherenkov light because it has like a blue glow. And it happens only when the particles travel faster than light in a medium. I will say it again. Cherenkov light happens when a charged particle travels faster than light in a medium. So we have this idea and this conception in physics that the speed of light is it's a limit. It's the fastest that you can get in the universe. In vacuum. When it travels in a medium, it can be air, water, ice, or something transparent. Particles can travel faster than light in that medium. And if it's a charged particle, it produces this glow, which is called Cherenkov light. And to explain it, it's like the airplanes, the jets, for example, when they go above the speed of sound, you see a sonic boom. You can hear it, poof, the Concorde, the jets, and then you can name this. They name it the match 1, 2, 3, 4, depending on how faster you go. So it's the same effect, but with light. And you see this blue glow, and it's very characteristic for gamma rays and very high energy particles that travel in a medium. There is a third type of detectors, which are also ground based, but these are more like particle detectors, but they're in a water tanks. So you put a lot of water tanks in a very specific place. It has to be at a certain height, and you have to put a lot of them just to detect these cosmic ray particles and gamma rays coming from outer space. Again, they will interact in the upper atmosphere. They will produce a cascade of particles. You have a lot of water tanks, so these particles will produce a glow, this blue glow, in the water tanks, and you will detect them because inside these water tanks there are PMTs, there are photomultipliers that can tell you what is happening. This is a map of the spots in which all these detectors are. So you can see it by color. The blue spots are the current operating gamma ray telescopes. So we have Veritas, Hawk, Magic, Hess, and there is also another one in Tibet. The green spots are the gamma ray observatories, like the future gamma ray observatories, which is CTR North and South. So it's the next generation of the Cherenkov telescopes. We also have Taiga and Lasso. And there is also another one called SGSO. So again, this is the map of the world, and you can see all the different places in which all these telescopes are based. Particularly, we are interested in, to put in simple words, to have a photo of the universe in gamma rays. We wanted this for a long time. All the satellites that we have been launching into space is just to take a picture, to take a photo of how does the universe look in very high energies. And this one is an animation. You can see two different images. One is from one of the satellites that I was talking in the timeline, the CGRO. And there was an instrument on board, Egret, who took the first picture. This was 91 to 2000. And then there was another satellite launched by NASA. And inside that satellite, inside Fermi, there is the Large Area Telescope, the LAT. So this is an image of 12 years of data. And you can see the difference. They look similar, but it changes the definition. Like we got a little bit more of definition. For people who like photography, it's like having a long exposure camera and you're looking at the universe and you're taking a photo that it's taking 12 years to take. So you leave the camera open, you have the long exposure, and you get your image of the universe at gamma rays and very high energies. So this is the Fermi one. And you can see there, all the little points, the red dots, are objects, are stuff that are emitting in gamma rays along the universe. And these are different objects. I'm not going to go into the details. We're going to hear more about GRBs, but these are pulsars, active galaxies, blazars, supernova remnants, and all. There is a whole variety of these objects, and someone can give a talk of any of these objects for 30 hours. And it will be impossible just to decide what they are and just to agree on what's the physics behind them. But you can see again in this picture of the gamma ray sky, all the different dots, all the different points are astrophysical objects. You can see that there is in the middle, like exactly in the like a horizontal line, which is the galactic plane. So that part in the middle is our own galaxy, are the gamma rays coming from the center of our galaxy. And then you can see that there are some spots that are brighter and bigger. So this depends on the source. Some sources are just brighter because they're close to us or because they're most energetic. And some dots are also bigger because it's in terms of size. They call it diffuse. So they are diffuse and they're like they're not points, but they are more like an area around the sky map. If you're interested in gamma rays, probably you're gonna like this. There are gamma ray constellations. So you probably have heard of the regular constellations, the one that you can see stars at night. But the people from Fermi, they're very creative, and they were bored probably at some point. So they created a map of the gamma ray sky, and they came out with 88 gamma ray constellations, in which you can find the Godzilla constellation, the Hulk constellation, the Eiffel Tower constellation. So there is a website in which you can go and you can actually have a look of the sky at very high energies with all the constellations that these people made up. And you can see there is the Black Widow spider, Pharos, there is Godzilla, the Enterprise. They're very creative. So if you want to know your sign in gamma rays, you can check the map. Going back to the presentation. Yes. These are the current telescopes, the ones that I was talking about. So Magic, Veritas, HESS. You can see there are in 3 different locations: La Palma, Spain, Arizona, USA, and Namibia. And the other stuff that is written there is basically technical stuff. It's technical details about how big the telescope are and how many detectors, how many photomultipliers are inside of the camera. So this is, again, if you like photography, it's like having like a good camera on your phone. If you have like a lot of pixels in it, every PMT will be a pixel. So if you get more pixels on your camera, you will get a better resolution. And the mirror is like having your lens. So if you have a big lens, you get a better image. You can make a zoom. The same happens with the gamma ray telescopes. The bigger you have the telescope, you can detect fainter light coming at night. And you can have an image at low energies from these objects that are fainter. So going to the next one. This is the next generation of telescopes. So these are the ones that are being built right now as we speak in La Palma and in Chile. And again, these are going to come in 3 different sizes. You saw the video. In the video, they explain each one of them has a specific design. Each one of them, it's like thought to aim at a particular thing. And that's why we have 3 different sizes. And that's why the designs have to be different, the cameras have to be different, the mirrors have to be different. So a lot of people have put just a lot of effort just to make this possible. And now it's finally being built. So it's a good time for gamma ray astronomy. If you want to know more technical specifications, how big are the mirrors, what are the cameras doing, how can you detect them, everything is on the website. So you can visit the ctao.org website, and they have a new brand website in which you can find all this information. They have information about the sources, so you can know more about black holes, pulsars, supernova remnants, etc., etc., etc. They also have the material to know more about the telescopes and the technology. And they also have interactive games. The last time people were presenting this in a conference, they have a virtual reality. They have virtual reality for gamma rays. So it's very interesting. If you are curious and you want to have a look at gamma rays, you can go to the website. So from all of this, also what you can take is the technology. every time a big discovery, every time a big project is built, there's a lot of technology coming out of it. So in the gamma ray, we have the cameras and the electronics. You heard the people in the video, these flashes of sharing of light are of nanoseconds. So they last 10 nanoseconds. It's like taking a very fast measurement. And the cameras that are on the telescopes can go down up to 1 nanosecond. So that's super, super fast. And you need special electronics for that. We also have flashes to calibrate the telescopes. Some people have done a very good job on the technology, on the electronics, on the flashes. There are also the mirrors for all the people who likes astronomy or are astronomers. It's really difficult to build mirrors that are big. If you go above a certain diameter, gravity is it's a bitch, and it's gonna break your mirror. And it's really difficult to build big mirrors. There are also the engineering part related to the telescopes. So it's more related to having a ton, like a very a very heavy object, move it at a very high speed. And if you like more the stuff related to computer science or data analysis, we also have that. So there is a little animation that it's like a gamma ray shower that is detected with this camera mounted on this telescope, and you can see there how are these green stuff passing around the pixels of the camera. So I'm going to conclude my talk here. I hope you know more about gamma ray astronomy. I hope you are interested more in gamma ray astronomy. What I will say is, in summary, gamma ray astronomy allows us to study the universe at the highest energies, including the hottest and most energetic astrophysical sources. Why is that important? Because by doing that, we can test our current knowledge about physics in extreme environments, and we also can search for new models. And I will finish everything with a quote. Science is not a collection of facts, it is a process of discovery. So that is what science is all about, and that's why are we building and why are we putting all this effort in building this CTAO. So I will say thanks for your attention. Thanks for your attention. If you like the talk and want to know more about physics and astronomy, you can follow me on Instagram. Or if you're old school, you can send me an email and check out the website. Check out the CTAO new website. There's a lot of good stuff in there, and you can, if you're curious, you're gonna like it. So thanks a lot.
Okay, so now it's time for people's questions. We have questions from the audience. Yes. Somebody? Okay.
So you mentioned that CTA has 3 types of telescopes: the small, medium, and large.
Yes.
Can you talk about what each of the sizes are used for? What each of the sizes are used for?
Are used to? Used for, yes, used for. So if I go back to the slide in which I have the sizes of telescopes, it's basically related to the size of the mirror. The biggest one, the ones that have bigger mirrors, are for low energies. There is like a range of energies. Yes. Yes. So you have the different sizes of telescopes. The biggest one is to basically observe objects, which we call low energy, the low limit, the low boundary of CTAO, which is around 20 GeVs. So it's gig electron volts. For you makes sense. For the people in the audience, it's just the faint objects that we can detect from astrophysical sources. If you go down to the middle size, then you are in the core of detection of CTAO. So basically, with those telescopes, we aim to see brighter objects, and you can go up to TeVs, tele-electron volts. And with the ones that are small, we basically observe the most brilliant and the most brighted one. So depending on the size of the mirror, you will use it to observe something that is very faint with the big size, something that will be in the middle range, which are the ones that we want to observe for a long time. And then the small ones will be for the most energetic part and the ones that are going to go like very, very extreme energies. And then the cameras, everything is well designed. So the cameras that are mounted on each of the telescopes are matching the design of the mirror, of the structure. So everything goes within the design. Sí.
Thank you for your presentation. It was very interesting. There was one part that really caught my attention, which was how particles are able to travel faster than the speed of light.
Yes. Yes.
Groundbreaking thing.
Yes.
So, so my question here, maybe it's like I don't know, naive or something, but one thing that I don't understand is if the particles is already traveling faster than the light in a source medium.
Yes.
When it comes out of the source medium, what happened to that velocity when this accelerates, or and just like retakes the speed of light again? And if that's so, what happened to that energy? It dissipates in the medium again, or like what happened there?
Yes, yes, yes. So what happens is that for example, when light travels in a medium, it changes the speed. Like we take it as a constant, but it's a constant in vacuum. But then when it travels through water, through air, through glass, or through any transparent medium, the velocity changes, right? So that's why the first part is that's why there are some particles that are very energetic, that are accelerated almost to the speed of light. And when they travel in that medium, they're able to go faster than the speed of light in that medium. What happens with that? There is this phenomenon, like the basically these charged particles that are traveling are emitting radiation. So when they travel into the medium, there are electromagnetic forces going around, and these particles are emitting radiation. So all the radiation that they emit is basically dissipating the energy of the particles. And then what happens when they change medium, like there are experiments that they do this with lasers. So you can have different mediums, you can have plastic, glass, water, and some other stuff. And you can point a laser to them and then put like at a certain angle. So you can see how the light bends a little bit when it's passing through the different mediums. The same thing happens to particles. Because when we think about light, at least one part of light, it's like a photon. So some physicists think about light as particles, as photons. And then the same description, the same mathematical stuff, you apply to electrons, protons, or other particles. And you can describe how they move through a medium. So when we think about light, we think about particles, we think about photons, and then we just apply that to the other particles. And we have the description of how they move in this medium, how they dissipate their energy, and how they're going to change the velocity from one medium to another. But it's like a really interesting effect that it's very visible for us, or we can notice this because of the blue light, this blue glow coming out of the charged particles. An interesting fact is it's called Cherenkov because it was observed by some Russian scientists. But also Marie Curie saw that blue glow. Actually, she was the first one to observe that blue glow in Paris. And I can't remember when exactly, but few later, it was discovered and documented by some Russian scientists. So they put the name of the person who discovered it. So it's Cherenkov because of that. But actually, the first person in history of Earth to watch at that blue glow, it was Marie Curie.
So there's a motion for Curie-Cherenkov light.
Yes.
Cherenkov light, right? And there are things in the past that have been changed, the names of equations or other phenomena. So maybe we can try proposing in the next astronomical international meeting. Do you have more questions? Okay, because not I will ask a question. I'm curious about the farthest away X-ray source that has been seen. I don't know.
I don't know. I'm not sure.
You don't know?
I'm not sure. No.
Yeah, but what are the far away things we can tell with X-rays? Yeah.
With X-rays, I don't know, or with gamma.
With gamma rays.
Okay. So there is a record. The biggest telescope, this one that was built inaugurated in 2018. It has the record for the farthest object that we have seen in gamma rays with the ground-based telescopes. I can't remember exactly the number, but it was like 1.2. We measure everything in astrophysics, in astronomy. We measure everything in terms of redshift. So instead of giving a number that it's super big, that it will be like millions of kilometers, we say just a number which is called redshift. And the record is for this one, the biggest telescope, the large size telescope, and I think it's 1.2. To put that into context, if you look away, like if we observe something on Earth, that's redshift 0. If we observe something in the Big Bang, that's redshift infinite. And the record of records, like the telescope, space-based telescope that is supposed to be the best one to observe this kind of stuff, is the James Webb. And they claim that they can observe up to redshift 14. With this one, we can observe 1.2. With the stuff that I have been working on, which is simulation, it's not real data. According to my simulations, we will be able to observe with no problem up to redshift 2. But again, this is a little bit speculative. What it's on paper, what is real, coming from the data is the biggest telescope, the large size telescope, has the record right now, and it's 1.2 in redshift.
Thank you. Any more questions? Okay.
I was wondering if, as pop culture would lead us to believe, such as the Hulk, if gamma rays
Yes.
are actually harmful to, such as mediums, water and whatnot, or even just for a basic level on humans, is it actually that bad if anything is exposed to it?
So, in terms of gamma rays, like it's radiation, and anything that is radioactive for human beings, it's bad. So, if in real life something like the Hulk, like something like what happened to Dr. Bruce Banner, happens in real life, he's going to be dead. Like, if it happens to any of us, we're going to be dead, because our body, it's going to absorb that radiation. And what happens when you absorb that radiation is, if it's gamma rays, it's going to break your DNA, and then your body can tolerate a certain amount of radiation. You can see this with people that do radiotherapy in hospitals. Your hair will fall down. Your cells are going to be damaged from the inside. So it's not like you're gonna feel something at the moment, but then after a while, your hair is gonna fall down. You're going to start bleeding from your eyes, from your nose, internal bleeding. Your cells, your system, everything is going to fall apart, and then you're gonna die. How do we know this? Unfortunately, there were nuclear bombs. There were the nuclear bombs in Japan, Hiroshima, Nagasaki, and the people who lived there at the time were exposed to radiation, and they experienced all of that during the explosion. So the people who were not killed by the explosion itself, by the heat, by the burn, they were suffering this type of stuff in the days after, and then unfortunately they died days or even up to 2 weeks after. So if you are exposed to radiation, to gamma rays, it's harmful for your body. It's gonna kill you. You're not gonna turn into the Hulk. And what I will say is, in any case, if you're turning into the Hulk, you should be blue because of the sharing of light. You should not be green. Yeah, but that's in general. Not only with gamma rays. Like if you are exposed to radiation, an isotope like a radioactive isotope, uranium, cobalt 60, plutonium, is bad for your body, and you can only tolerate a certain amount of radiation. After that, you're dead. You're walking, but you're dead.
Okay. Ooh, we have more questions? Oh, okay.
When you say gamma rays are the highest energy radiation,
Yes.
is there a physical constant or limit about of the electromagnetic radiation? And if yes, up to what point is that gamma ray close to that constant?
Yes. Okay. So when I was showing the electromagnetic spectrum, there was this like line in which you can go up into higher energies. So in principle, there is no limit. Like you can go as high as you want, but there are some physical constraints. So to produce this type of stuff, you need astrophysical objects, which are like massive particle accelerators. So I'm talking about black holes that are millions of millions in terms of size, bigger and heavier than our sun. So you need like a cosmic scale just to produce this type of particles and this type of accelerators. There are also other constraints. The space, yes, it's vacuum, yes, it's empty, but it's not really empty. It's full. It's full with radiation, with dust, with neutrinos and other type of particles. So specifically speaking, radiation and dust, it's like if you have like a very high energy particle, it's like going into a cloud. It's going to be opaque, and you will not see the most energetic particles. So even if they are created, just because of the universe, just because of the nature of what's inside, they will interact with light, with dust, and then we will not be able to see those most energetic particles. So that's the basic idea, yeah.
Okay, so I think it's time to celebrate Alberto again.
Thank you.
So much. We are going to take a break, and we'll be back with more.
Let's take a break.
Ooh, so let's take some years.